Okay, so hello everyone. My name is Baransky and I am going to present the paper titled Mitigation of Fake Data Content Poisoning Attacks in NDN using Blockchain, co-authored by myself and Professor Jerzy Konorski of Gdańsk University of Technology in Poland. I will start with a short introduction of information-centric networking, then outline the problem of fake data content poisoning and its proposed solution called proof of time. Next, against the background of an existing proof of time method based on graph infection, I will present our proposed method based on blockchain. Finally, the two methods will be compared. Current TCP/IP architecture allows connection-oriented or connectionless data transfer between specific IP addressable interfaces. Such a model is struggling to fit current internet demands. The internet of today is dominated by transporting content such as websites, audio and video from multiple content creators to content consumers. Information-centric networks, or ICNs, respond to this challenge with a paradigm shift from host-oriented to content-oriented. Among the most significant benefits is content caching. Content caching or in-network storage permit to keep publishers' content close to interested subscribers. This saves bandwidth and reduces latency, but also introduces new attack vectors. An example architecture of named data networking, which will serve as a conceptual framework throughout the rest of this presentation. In the end, uses two types of packets called interest and data. Interest packet is request for specific content, referred to by a unique identifier and some optional selectors. A data packet returns the requested content along with a publisher ID and a signature to guarantee content integrity and authentication. The NDN node functionality on a network device is as follows. When an interest packet is received on some node's input phase, the node checks if the requested content is present in a local cache, the content store. If not, then the request is placed in a pending interest table where it waits until the content becomes available. Next, the node looks up the forwarding information base for the direction in which the content is likely to be present, and forwards the interest packet through that phase. Upon receipt of the response in the form of data packet, the request waiting in the pending interest table is removed, and the data packet is forwarded through the original input phase. The problem lies in the authentication model based on publishers' signatures and content caching. It is a double-edged sword, powerful but at the same time potentially dangerous. Namely, it makes the fake data content poisoning attacks possible. An attacker who has stolen the legitimate publisher credentials, for example private key, is indistinguishable from the legitimate publisher, therefore can create poisoned content. Such poisoned content cannot be easily identified by the network or subscribers, as information-centric networking systems mostly do not allow removing or revoking of cache content, except for natural cache aging mechanisms such as less recently used. The problem becomes solvable when we make some plausible assumptions. First, the attacker is time constrained, that is, eventually loses access to the stolen credentials, either due to expiration or some administrative actions on the part of the credentials owner. A legitimate publisher, on the other hand, has unrestricted access to his or her credentials. We leverage those assumptions to claim that a publisher able to prove access to credentials over some period of time is trustworthy, and one unable to prove that is untrustworthy. More formally, the traditional authentication model states that access to credentials implies content authenticity. What we propose is an extension whereby not only access to credentials, but also, so to say, access to time is required to imply content authenticity. We call this approach proof of time. It remains to specify how to prove access to time. We propose a mechanism of periodically checking in. And by checking in, we understand performing an operation that requires access to the credentials. If extended over some period of time, periodic checking in is equivalent of having access to the credentials over that time, which constitutes the postulated proof of time. Proof of time must be located at a place trusted by both parties, the publisher and an interested subscriber, and a method of its creation must be designed. An existing proposal presented at last year's ITNAC conference uses a graph infection mechanism where each ICN node can be infected by, that is, trust a given piece of content. We propose here a novel method based on blockchain to be presented further. In the graph infection method, a publisher willing to prove access to credentials over some period of time has to perform a series of publications called external infections, each time presenting credentials. The process is controlled by the network to force the publisher to perform it sequentially. Each externally infected node introduces some delay, and a certain number of external infections is needed to infect the whole network, so that the publisher needs sufficient time, access to time. In contrast, we propose to use a blockchain network as a storage for proof of time. It is assumed to be a trusted place where proof of time claims are immutable and secure. They are next used to produce a credibility score for each piece of content. A proof of time claim is represented as a blockchain transaction consisting of the publisher public key, a hash of the content to be authenticated, a pointer to the previous block hash which prevents pre-signing transactions, and a signature which proves access to the corresponding credentials. Publishing and authenticating content consists of the following steps. First, publisher creates a named data object, NDO, which is an NDN primitive. Such an NDO can be then published to the ICN node. Next, in order to authenticate the NDO, the publisher creates a series of proof of time transactions. For each, computes the hash of the NDO, his or her public key, and the previous block hash. Finally, signs the whole transaction using his or her private key. Such a transaction is then published to the blockchain network. We call the number of proof of time for particular content a credibility score. Different types of contents may require different credibility score values. For example, a banking record will require a much higher credibility score than a weather forecast. The publishing process is repeated periodically until a sufficient credibility score is achieved. Now, when a subscriber wants to fetch and verify a piece of content, he or she first sends a suitable interest packet to a ICN node, and in return gets a data packet. Then he or she asks a blockchain node for a credibility score for the content, producing the respective publisher public key. Finally, the blockchain node returns the credibility score, which the subscriber interprets and decides whether to trust the content. Here we can see an example where three publishers try to publish a sequence of proof-of-time transactions. Alice is marked in red, Bob in blue, and Carol in green. If we assume that the blockchain produces a new block each 10 minutes and we require a 20-minute proof of time, then Alice successfully proceeds with 3 publications, reaching the 20-minute threshold. Bob, on the other hand, published only 2 transactions, proving only 10 minutes access to time. And Carol publishes 2 transactions, but with 1 block gap, which is considered a chain break. As a result, her chain starts anew from 3rd block. Our framework does not constrain where the blockchain layer should be deployed. We consider two scenarios. One in which the ICN transport layer and blockchain trust layer are integrated, running in parallel on the same network nodes. Alternatively, those layers can be allowed to run separately, achieving better portability across different ICN solutions and relieving the network operators from installation of blockchain node functionality. If we compare the blockchain-based method with the earlier proposed graph infection method, we can notice some improvements. First, we have outcome determinism, which means that a publisher with sufficiently many proof-of-time claims is certain that his or her content will be authenticated, as guaranteed by the safety property of blockchain consensus. While an outcome of the graph infection algorithm in general depends on chance. Our blockchain solution is also more resilient, meaning that unlike the graph infection algorithm, it is independent of the network size and a number of infection parameters. There is just one assumption regarding the existence of quorum intersection, as required by the adopted stellar consensus algorithm. Finally, blockchain consensus ensures a degree of fault tolerance, permitting to continue correct operation in the process of Byzantine faults in up to 1/3 of the nodes. These advantages comes at the cost of higher communication complexity. In blockchain, each node has to communicate with all other network nodes. So the communication complexity is quadratic in the network size. Next, lower processing scalability, measured in the total content the network is capable of processing at a time. The reason is that in blockchain, each node has to process each piece of content sequentially. As a result, adding more nodes to the network does not increase the processing capability. Lastly, our solution requires additional infrastructure to be deployed, namely the blockchain network. To conclude, our method compares favorably with graph infection regarding outcome determinism, resilience, and fault tolerance, at the price of extra infrastructure required. We are currently working on simulation in a realistic NDN environment to investigate content delivery latency and communication cost. And that completes my presentation. Thank you. If you have any questions, you can ask them now or send them to me via email.
Thank you, Stanislav. Although out of curiosity, I was just wondering, in the presentation you mentioned Omnet++ and NS2, right? Is there any reason as to why you're not using NS3?
Yes, because one member of our team knows better NS2. So he decided to use NS2.